Hi everybody, today we are looking at something a little bit different, but actually a lot the same. So far, we have seen that d equals vt, displacement equals velocity times time, is a way to describe things that are moving at a constant speed. We also sort of rewrote this equation a little bit, and we wrote it as v is equal to the change in displacement divided by the change in time. Let me clean that up. That's kind of messy. V is the change in displacement divided by the change in time, which we said was d2 minus d1 and t2 minus t1. And we made a little shortcut with the t's because we realized that t1 is almost always a 0. So we kind of turned it into this, showing us the change in position or the change in displacement on top and the change in the time in the bottom. Okay? Good, but that's all the same thing. Those two equations are not different. They're just two different versions of each other. And often we just use this version over here and we just kind of understand all this other part in our head. Okay, but there is a very important note that I'm going to write here in bright purple. These two equations, or these two forms of the same equation, are only for describing constant speed, speed that is not changing. Constant speed. Or we could also say constant velocity. So they become difficult to use or impossible to use if the speeds actually start to change. And that's what we want to look at today. We want to look at what we can add to our toolbox of tools here that might help us describe what happens when speeds change. And of course, that means that what we're talking about is acceleration. Acceleration is the rate of change of velocity. The rate of change of velocity. So when we talk about the rate of change of something, remember that's a comparison with how the time changes. So what this actually means is, if I were to write it another way, in other words, i.e., it means that acceleration is equal to a comparison of the change in velocity compared to the change in time, right? And I'll write that over here in words. It's the change in velocity because we want to make sure we can translate our English and our math. The change in velocity, delta V, compared to the change in time. And of course, when you look at this equation, it's a delta V over delta T. It's very much like our delta Y over delta X. So what this means is that this is a slope. It's a slope equation. But it's not the slope of a displacement time graph. If you have delta Y over delta X, right, our Y now has to become V. So now what we have to do is, it's the slope, but it's the slope on a velocity time graph, a VT graph. So let's have a look at what that might look like. If we draw a simple graph, I'm going to draw a couple of different graphs here. Here's one. And we draw some object. Let's say that the graph is graphing velocity, V, and time, T. And we put an object here moving at 5 meters per second. Well, if it doesn't change its velocity, it would just go straight at 5, never changing, never changing, never changing. Forever. And that would have a slope of 0, which means there is no change in the velocity, which means there is no acceleration. Now, let's just see what would happen if we picked a certain time. I'm going to just pick it here. I'm going to call this the time t, right? And I'm just going to go like this at that spot. Let's say we wanted to know how much distance this object, or what the displacement of this object was at this particular time t. So let's ask ourselves, what is the displacement at t, the time t? If you're going at 5 meters per second and not changing. Well, we know how to do that. We know that d equals v times t, right? But I want you to look at what's happening right here. There's an interesting mathematical thing happening here. We call it multiplication. Well, multiplication is actually a very, very commonly used operation, but let's think about what it actually does. We may have never thought about this before. Let's think about another place where we multiply. If I wanted to discover what the area was of the rectangle that's made by this blue line and the t-axis, so if I color in the area like this, well, then normally what we do for area is we consider this to be sort of what we would call the length. And then this part up here would be the width. And area equals length times width. But look at our graph. Our width is actually a measure of the speed. This is actually on the graph, and it's over here. It's the speed at which you are going. And time happens to be on the graph. The length, if you look at this again, there's the length. Well, look, it is the time times t. And so the area of our graph becomes length is time, and width is displacement. Or sorry, speed. Look on the graph, it's speed. Let's not get too carried away here. Well, what is v times t? V times t is the distance. So what we've discovered is that when we do this little d equals v equation, we're actually calculating an area. And it's the area under a vt graph that we're calculating is displacement. That's a very important thing to remember. I'm going to put a box around it. Now we can explore this idea a little further. The fact that if you take the area between a line on a VT graph and the time axis, then you can figure out the displacement. Right? Okay. So let's see what we can do with this. We can do a couple of things. Now I'll draw a second graph. This time I will draw an object that starts at the speed of 0 and speeds up like this. So that over here is the second speed at which it's moving, and down here is the first speed at which it's moving. And of course there would be a certain amount of time that it would take to speed up from one speed to the other. So again, we're talking about a velocity and time graph. Well, we've already said that the slope of this line, the slope is equal to the acceleration, the rate of change of velocity. This acceleration is equal to the slope of this line, which would be delta v over delta t, which basically means that a is equal to v2 minus v1 over t2 minus t1. But just like before, if t1 is going to be 0, then we can make this in a little bit simpler form, as long as we understand what we're doing. The change in speed over the amount of time that's taken for that change to happen. Okay, so we have this new slope equation, right, which looks very much like the equation for velocity. The two of them look very similar. Let me go back up to the very start here. When I showed you the equation for, there's the equation for velocity. Compare that to the equation for acceleration. The reason they look so much alike is because they are both slope equations. One is the slope on the dt graph, the other is the slope on the vt graph. Okay, let's leave that for a minute. Let's also then look at what we said was the area. Well, this area is a different area. It's not a rectangle anymore, is it? It's, let me see if I can shade this in a little bit. I'll take this, and I'll shade in red. It's the area all under here. This is the area between the red line and the time axis. But we've already said that on a VT graph, area tells you displacement. We've shown that. So now it's going to tell us displacement, but it's just going to be a different shape. So let's explore how we would do that. I'll move this up a little bit, and we'll just look at this. In this case, the area, which is the displacement, I'll put that over here. So the displacement is the area. But the area here is not length times width. It's 1/2 base times height, because it's a triangle shape. So let's figure out what the base and the height are. Well, here's the base. The base is the amount t. And here's the height. The height is the difference between v1 and v2. So I'm going to write v2 minus v1, right? That's how you'd figure that out. Now, since v1 is 0, it's basically just v2. But we'll put it this way because there's nothing saying v1 always has to be 0. Let's write our equation then. The displacement, which is the area, is 1/2 of the base, which is t, multiplied by the height, which is v2 take away v1. All right. Now, to make things simpler, I'm going to go back to my other equation, right over here, that I had written before. And I'm going to mess with it a little bit. If I take this equation and I multiply both sides by t, I can turn it into this. And this tells me that the v2 minus v1, whatever that works out to be, has to be the same as a times t. So if they're the same, they can be interchanged because they're not different. So if I go back over here, I can do in math what we call substitution. And I can replace v2 minus v1 with at because they are the same. And so I will substitute or replace that, and I will get this. That's the same thing. And of course, if you multiply that out, it turns into this. D equals 1/2 of a times t, or t squared. So this is an equation that is telling us something about the displacement, d, in terms of the acceleration rate of the object. But we're not quite done, because as I said before, v1 doesn't have to be 0. You see here on the graph, it starts at 0. What if it doesn't? Let's take this one step further and see if we can't make it just a little more sort of universal, so that it would work for anything. So let's take a graph again that looks like this, but this time we're going to start the graph here at this v1. And we're going to get up to v2, and we're going to start going. So this might be a little cat walking along the side of the road at v1 speed, but then perhaps it sees a dog and gets scared, or chases a squirrel, and it runs up faster and faster and faster until it gets up to the v2 speed, which is this. So it speeds up, it accelerates. And of course, there would be a certain amount of time it would take for that to happen. And we should remind ourselves that this is a velocity time graph, obviously with the v's and the t's. Well, now I can say the same thing. I can say that the area is equal to the displacement. But the area is a little more complicated because you'll notice I have two shapes. I have sort of a green shape. I'm going to make it green on the bottom, which is a rectangle shape. So I have to get that area right here. Whoops, the wrong color. Wrong color. Let's go green. I have this area down here that has to be considered. And I also have the area above it, which is a triangle. See, it's the area between the line we've drawn, the red line, and the black t-axis. So I also have this triangle area that has to be accounted for somehow. So I have to add up two areas to get the area of this. So that's what I'm going to do. I'm going to say that the displacement, which is the area, and I'm going to do this in black, the displacement is equal to the green area, length, times width, plus the red area, which is 1/2 base times height. And so if I plug in what I've got, well, the length of the green area is a t, and the width of the green area is actually just, if you look on this side, it's just whatever V1 is. V1. That's how high that would be. So for here, I can write width times length, or length times width. We usually write it this way. It's V1 times t. And then plus the red area, which is 1/2. Now, here's the base of my triangle. But notice that that's also just t on the t-axis. And here's the height of my triangle, which is, if I squeeze it in here, V2 take away V1. That's what we did last time, remember? In the other example. So here I have t times V2 minus V1 for the triangle. But we also said that V2 minus V1 actually equals AT. So if I go down here, oops, if I go down to the very bottom here, sometimes technology doesn't do exactly what we want. Here we are. So here's my graph. I can rewrite, I'm going to go jump, there's a t in the way there, I'm going to jump down here so it doesn't get confusing. This becomes V1t, and then instead of this part, I can substitute AT for this. We've already shown how that can work, so I won't write it again. So this becomes 1/2 A times t squared. And this is a very useful and important equation that we will keep, because it tells us how to determine the displacement of something if it happens to be accelerating. It's got A involved, if its speed is not staying the same. And of course, if the initial speed is 0, well then this term here would be 0 times t, and it would become 0, and then it would look just like the one that we had done up above, right here. But this one is probably not the best one to keep, because the first speed doesn't have to be 0. So in this case, this will work for that, but it will also work if the first speed is 10 or 9 or 107. It doesn't matter. So this equation is probably more comprehensive. It covers more stuff. So what have we learned so far? We've learned that we have two new equations. We have acceleration, which is the change in velocity compared to the change in time. It's the slope on a VT graph. And we have learned that displacement is equal to V1t plus 1/2 of AT squared, because it's the area. We've learned about slope, and now we've added in area. Two very important graphing things, mathematical concepts, that give us these relationships that we can use. All right. And that's as far as we'll go for now, and then we'll get some practice in using these two equations.